Hello everyone, I'm Anirudh. I'm a Chennai IIT and I am currently a third year undergraduate student in the Department of Computer Science and Engineering. Enrolled is a Bachelor of Technology course, 4 years in Indian Institute of Technology, Kharagpur. Right? So today I'll be taking the lesson differential equations. That's chapter number 9 for all of you who can't see my screen probably. In class, this is class 12 NCERT. Right. So first of all, I'd like to give you a brief. Right. For maths, what I usually do is I give a brief up to the topics that that is going to be covered in the next exercise. So that is pretty fresh, and it's also kind of like a primer before I go into the actual exercise. Right. So first of all, this differential equations. What it deals with is what it deals with is the use of differential calculus and differential elements in normal equations of mathematics, right? So, for example, this is mostly applied in practical physics, right? And even in theoretical maths, but you don't really see that in class 11 and 12, but you usually see it being used, right? Where you usually use differential equations for even velocity and acceleration. Right. So when you say that these are dx by dt and you basically substitute that in any equation and then go ahead and cancel out dt terms or go ahead and integrate somewhere somehow something and you finally get an answer. Right. For example, your a third degree equation of displacement and time, where you can't really say that the acceleration is constant, and so you have to integrate and find out all your values. Right? Those kinds of equations are places where you use differential equations, because that essentially is a differential equation that you're going to solve. Right? That is basically some kind of an application that you use in everyday life in class level, right? Because in maths you don't really see the use of differential. So that is basically where you do it, and why you do it is because it simplifies your life. Right? Instead of taking up different terms and then summing up over very infinitesimal quantities, you can basically differentiate it. Okay, that's basically used. And why an equation? Because they are pretty complex quantities. You need to find out relations, etc., etc., so on and so forth. Right. So what this introduction deals with is a basic concepts of differentials, right? Where you know what dy by dx is because you would have studied differential calculus before you go into differential equations, right? You know how you use that. Use that sometimes in equations when you equate something to this variable value, right? So you know the different representations, you know the different notations, and then you know that what exactly the NCERT textbook also uses for these notations, right? Here, first thing, you figure out what the order of a differential equation is. The order is basically the highest power of this dy by dx term, right? The highest power to which it's taken, right? No, it's the highest degree to which this y is differentiated. That is the order, right? The degree is the power to which this highest order term is taken to. So, for example, in this equation, right, your degree is in this equation, your degree is basically 3. Your degree is 1. Your order is 3. Right? You can't take this term because this is y double dash, this y triple dash, this highest order term, this order 3. Right? And this term has a degree 1. Right? This basically like how you find the degree of your normal polynomial equation y square plus y plus 1 equals 0 has degree 2, right? Because that's the highest power of y. Here, you basically say that this if you have a differential equation of the form y100, that is the 100th derivative of y, plus y2, that is the second derivative of y, plus 3 equals 0, something of this sort, right? Because this is a valid differential equation. I don't care what a solution is, right? Or even if it has a solution, but this is a valid differential equation, right? This has an order of 100, a degree of 1, and that basically takes care of the two different things that you have. Right? That's basically what this is. You can basically compare it to this kind of a polynomial form where this can, if you want to complicate things a bit, you can say that this has a characteristic equation of y power 100, or instead of y, I'll write it as, wait, can I say that it's x power 100 plus x squared plus 3 equals 0, something like this, right? Bring out this thing up over here. Then you can basically say this and say that the order is 100, something like this. That's but that's stupid. No. Just see what's given and take your order and things like that, right? That's the order and the degree taken care of, right? Again, saying order is the highest, the order of the highest order derivative or the dependent variable with respect to the independent variable, right? Basically, here is 3, here is 2, here is 1, right? Degree is the highest, the part 2 is the highest order derivative as the exponent of the highest order term, right? This is y triple dash. Degree is defined over here, and you should know that degree is only defined for polynomial differential equations, not for something like sin y dash equals something. You don't this kind of term does not have a degree, right? Because degree is only defined for polynomials, right? This is of degree 1. This is of degree 2, and this does not have a degree, right? So I mean that's a part of exercise 9.1. So I just go with 9.1 now. 9.1, right? Determine the order and degree of the differential equations given in 1 to 10, and 11 and 12 are 2 MCQs, right? First question. First things first, look at if it's a polynomial, right? It's not a polynomial. You don't have a degree, right? No degree defined, right? But for non-polynomial differential equations, you do have an order, right? The order is the highest power, highest order differential, highest n differential, right? And here is as 4. The order is 4, right? Instead of now writing like no degree and order is 4, I'll just represent degree by D, order by capital O, right? Just give me a sec. And by no degree, what I really mean is a degree is not defined, right? Don't write it directly as having no degree. Say that the degree is not defined, right? Here is because it's be easier for me. I'm writing with this, but what I mean by this is that the degree is not defined. Right? Number 2, again, number 2 is y dash plus 5y equals 0, right? Y dash plus 5y, easy to see that it's a first order differential. Here O equals 1, and since the power of y is 1, y dash is 1, the degree is also 1, right? Question number 3 says that it is S4, ds by dt power 4 is S4, right, as given over here in the notations, right? For yn is the nth order derivative dny by dxn, right? So I'm going to use shorthand everywhere. Don't get confused, right? And it's 3s into s2 equals 0, right? Wait, what am I doing? Sorry. S power 4 is S1 power 4, right? And plus 3s into s2 is 0. This is linear, right? This is a polynomial. This is not something like a non-polynomial, right? So you can see that number 1, the order is 2, and the power of this highest order term is 1. So over here, your order is 2, the degree is 1, even though you have an S1 power, right? The order is 2 to be 1. Question number 4, right? This is y2 squared plus cos y dash, right? And this is 0. Again, this is non-polynomial because it's cos y dash, right? This, you can say that the order is 2, but the degree is not defined. Phi says it is y2 equals cos 3x plus sin 3x, right? Again, x terms do not matter, right? Because the dependent variable is y, right? So this, for all intents and purposes, this is a linear equation, right? This is a linear polynomial. So from here, you get that the degree is 1 and the order is 2, right? Only when there is some kind of a cosine or a logarithm attached to this y dash or y double dash or whatever, some differential term, only and only then you say that the differential is non-polynomial. Otherwise, the differential is polynomial for all intents and purposes, right? Even though it may have some kind of cos 3x, sin 3x, or some kind of some cos 3y or something like that, right? Nobody cares if the term inside the cos or the sine or the log or the ln or the e power whatever is a non-differential in nature. So that's question number 5 and the note I wanted to talk to you about. Question number 6. It's y3 squared plus y2 cubed plus y1 power 4 plus y power 5 equal to 0. Right? Again, we don't care about all the rest of the terms. Highest order term, degree, right? And if it's polynomial. Well, no brainer, that's polynomial. Degree and order are well defined, right? From here, you get that the order is 3. And same way, you get that the degree is 2. Question number 7, right? y3 plus 2y2 plus y1 equals 0. Same way, linear polynomial. So the order and degree are well defined. The order is 3, the degree is 1. Right? Question number 8. Y dash plus y equals e power x. Right? You'll learn how to solve this kind of an equation further, but for now, pretty easy to see that this is polynomial, right? Because e power x for all intents and purposes is a constant, right? We don't really care about it. Right? The differential is linear, is polynomial in nature. So the order and degree are well defined. The order is 1, the degree is 1. Right? Question number 9. 9 is y2 plus y1 squared plus y into y equals 0. Right? Again, pretty easy to see that as polynomial in nature. Order and degree are well defined. The order is 2, the degree is 1. Because y2 is your highest order term. Right? And lastly, question number 10, which is y2 plus 2y1 plus sin y equals 0. Again, I told you, sin y, since it does not have a differential term, does not really matter, right? This differential is polynomial in nature. And so the order and degree are well defined. The order again is 2 and the degree again is 1. Finally, coming to the 2 MCQs, the degree of the differential equation blah is not defined because you have a sin divided by x term over there, right? Because of this term, you have a non-defined or a not well-defined degree. I will say why in a minute, right? Just let me complete this. Right? And finally, the order of the differential equation blah is what? Simple. Take the highest order term, order is 2. Right? Because it's d squared y by dx squared. So the order is 2. Right? Why exactly is this kind of an equation have a non-defined degree? Right? Since all of you have come to differential equations, you should know that each of the trigonometric and the other special functions, they have infinite expansions, right? You may have heard about the Taylor series or the Maclaurin series expansions, right? The most famous is the Taylor series, right? I think you'll also have an appendix note about this in the NCERT maths textbook also, maths class 12. I'm not sure about that. Right. So you have some kind of series expansion called the Taylor series, which exists for any kind of a special function, right? Where this goes like a function f of x can be represented as f of 0 plus x by 1 factorial f dash of 0 plus x squared by 2 factorial f double dash of 0 plus whatever up until infinite, right? So this is basically an infinite expansion where you have powers of x up until infinity, right? And you have the differentials of f up until infinity, right? For this, you usually assume that the function f you are taking is infinitely differential, right? If you don't know what it really means, don't bother. Don't bother just finding it out. It's pretty intuitive, right? It basically means that how many ever times you differentiate f of x, you get a well-defined function and not some kind of a discontinuous or some kind of a point function. I didn't get that. You get a real function, you get a well-defined function. That's what infinite differential means, right? So here you can see that you basically have powers of x up until infinity and differentials of f up until infinity, right? And so basically if you have this kind of a sine divided by dx term and you use the Taylor series or the series expansion of this, then you get something that has a degree of infinity and a and an order of infinity, right? This actually condenses to form this sine divided by dx. So you basically say that the order is this term, right? But the degree, on the other hand, is something that's not well defined over here because differential, the expansion form is categorical, right? Right. So we have found what the order and degree of differential equations are. Now we move to how you solve differential equations, right? So two things, right? When you solve a differential equation, you get two kinds of solutions. That's a general and a particular solution, right? You have a big story over here as to what they mean, right? And they have actually, kind of equated that to some kind of a solution given by this y equals a sin x plus some kind of this, right? Now, what this basically means is that when you kind of take this equation, for example, this equation, right? When you solve it using some kind of methods that you'll study later on, right? You get some solution that exists in this box, right? Some solution which is general and has this plus c constant over here that generally depicts an envelope of curves that is called the general solution. But sometimes what happens is you also have some set of solutions over here like 1 and 2, right? These two are two different solutions that do not come under this general curve but are very particular to that example, right? Only if this differential equation is given, then these two curves satisfy that differential equation. Otherwise, if you basically change this even by 1 unit, these two solutions will not hold, right? Those kinds of solutions, if they don't come under the general curve, they are called particular solutions, right? And they exist only for these kinds of questions. That's basically the difference between the general and particular solution, right? Where right? So basically, the general solution has many arbitrary constants, right? And you can substitute whatever value for the constants, and you'll get some function that satisfies this equation. But here, these particular solutions do not have any arbitrary constants. They are very particular functions, and they cannot change, right? So they are called particular solutions. That's another difference, right? And that's how you generally separate between a general and a particular solution. Usually, every differential equation has both. Has both general and particular solutions, right? And you will see how to find them out. Just wrapping your head around it, right? Look at all these examples because they are very important, very vital, and they give you an idea as to how you proceed to questions, right? Cool. Exercise 9.2. Question number 1. Verify that the given functions explicit or implicit is a solution of the corresponding differential equation. You are already given the solution and you have to verify that it is actually a solution for the given differential equation, right? Right. Okay. So you basically have this y double dash minus y dash equals 0. Or you can rewrite this to form y double dash equals y dash, right? From this, I can get y dash equals e power x, right? Basic differentiation plus means that you can differentiate each of these separately. d by dx of e power x is e power x, d by dx of 1 is 0, right? Because it's a constant. And again, y double dash equals y triple dash equals y whatever equals e power x, right? Because y dash is e power x and y double dash is basically d by dx of y dash. This is e power x, right? So you can see that this is true. And so first one is true. This is verified. This is a solution of the corresponding differential equation, right? Next, number 2, y equals x squared plus 2x plus c. 2 y dash equals 2x plus 2, right? Easy. So you basically have this kind of an equation where you are given that y dash equals something, right? So differentiate this, y dash equals 2x plus 2. Basically, differentiation of a constant is 0. X squared gives 2x, 2x gives 2, right? So again, matches, verified, so it's true. 3, 3 is y equals cos x. Shit. 3 is y equals cos x plus c, right? And you have the corresponding equation, y dash equals minus sin x. No brainer, right? Differentiate, you get y dash equals minus sin. You get y dash equals minus sin x, right? Because c becomes 0, cos x is minus sin x directly. Matches, again verified, true, right? 4 is that y equals root of 1 plus x squared, and the equation y dash equals xy divided by 1 plus x squared, right? This is a little tricky to bring your equation in this form, but it's pretty easy to do, right? Because again, on the left hand side, you have only y dash, right? So differentiate once. This is y dash equals 1 by 2 square root 1 plus x squared over here into 2x, right? Chain rule, right? First of all, you differentiate root x. This is 1 by 2 root x over here, right? And then nx bar n minus 1 rule, right? N is half and n minus 1 is minus half. So it's basically 1 by 2 into x bar minus half, that's 1 by 2 root x, right? So you use this to get 1 by 2 root of 1 plus x squared. And then you differentiate 1 plus x squared, that basically gives you 2x. 2 cancels out. This is basically 1 by square root 1 plus x squared. So over here, this is basically square root 1 plus x squared. Wait, this is x by after 1 is x, I'm sorry. So this is basically x root of 1 plus x squared divided by 1 plus x squared, right? Rationalize the denominator, right? So this is basically xy divided by 1 plus x squared. Forgetting that, you can just basically write this as x by y, whatever. And this is this form. They match, so the equation is correct. Okay. Question number 4. Now question number 5. Y equals x, a times x, along with the differential equation x y dash equals, wait, x y dash equals 5, yeah, where x is not 7, right? If x is 0, whatever be the value of a, this becomes true, right? Because this is 0, this becomes 0. So x is 0 is a trivial case. You don't really deal with that. X is not 0, right? So over here again, you have this trivial first order derivative. So basically, you only need to deal with y dash, right? Y dash is a, right? X y dash then becomes ax, which is y. This is this equation, so it's correct. Also verified, right? Number 6, y equals x sin x, right? And y is given with the equation x y dash equals y plus x root of x squared minus y squared, right? X is not 0, x is greater than y, or x is less than minus y. Why is this important? This is because if x equals 0, this is 0, y is 0, and so both sides become 0, right? Trivial case, you don't deal with that. And this x, this condition, y literally means that this root is real, and it's not imaginary, because this has to be greater than 0. So you need this condition, right? I'm not writing the conditions down. because they're already given. But you should remember this. And they are right. And basically just strike them out and go off. So you have this. Again, you see that there is only y dash. So you need to differentiate this equation just once. Y dash is sine x plus x cos x, right? Which is sine x plus x root 1 minus sine squared x. Right, because cos squared x plus sine squared x is 1. Cos squared x is 1 minus sine squared x. And cos x is root of 1 minus sine squared x. Right. Now, if I want to bring this form out in every place, right? This basically becomes x sine x divided by x plus bringing this x inside is basically x squared minus x sine x the whole square. Right. So this is basically y divided by x plus square root x squared minus y squared. Right, because x sine x is y. Right. So finally, if I bring this x in the denominator to the other side, the equation becomes xy dash equals y plus x root of x squared minus y squared. And that is this equation. Right. So it's verified. It's true. This is question 6, right? Going to question 7. Give me a moment. Question number 7. You have xy equals log y plus c, right? Everybody should know that log y is basically log to the base ey, right? It's not log to the base 10 over here because in maths, log is natural log, right? Log and ln are the same. If and only if there's a base 10 mentioned over here, you take it as a log 10. Otherwise, it's always log e, right? So instead of log, if you write ln, no difference because maths treats both as same. In chemistry and physics, it differs, right? The conventions differ always. Remember, right? And y dash equals y squared divided by 1 minus xy. Cool. So this xy equals ln y plus c, right? Still you need y dash. So x is the independent variable, y is the dependent variable, right? And so when apply normal differentiation rules, right? Over here is a multiplication of two different terms, right? D by dx on both sides, d by dx into, right? What happens is that after this step, you basically get something like y plus xy dash equals d by dx of ln y is 1 by y into y dash. Yeah. And the differentiation of a constant is 0. Right? Y plus xy dash is basically y dash by y. That's what you're given. Right? And so you basically, if you rearrange terms, you get y equals y dash into 1 minus xy divided by y. Right? Because it's 1 by y minus x, I'm basically multiplying, dividing by y in this term and just taking the denominator common. Right? This means that y square equals y dash into 1 minus xy. Right? Finally, this basically means that y dash equals y square divided by 1 minus xy. Which is basically this. Right? So again, the same verified true. Right? Question number 7. Now going to question number 8, which is y minus cos y equals x as a solution to y sine y plus cos y plus x times y dash equals 5. Right? Again, you basically, you only have y dash. So you basically need to figure out y dash, differentiating on both sides again, is y dash plus sine by y dash equals 1. So this is y dash equals 1 by 1 plus n by, right? Over here, you can see that you have to bring this to the form y dash equals y by y sin y plus cos y plus x, right? And you have the fact that x is y minus cos y, right? So if you add an x over here, right? So if you add an x over here, right, I'll try bringing this equation to this form, right? First of all, you notice that you have a y in the numerator. You should have a y in the numerator to bring in this form, right? So I'll basically multiply and divide this whole thing by y. This is y by y plus y sin y, right? Then add and subtract x in the denominator, right? So basically, this is y divided by y sin y plus y plus x minus x, right? And substitute x to this, right? You have the fact that x is y minus cos y, right? So substitute that in this negative. Because you have a plus x over here, you have to substitute in the negative because this plus x is needed, right? This is equal to y divided by y sin y plus y plus x minus y plus cos y, right? Multiplying this minus into this becomes minus y plus cos y, right? And plus y minus y get cancelled. And then finally you are left with y divided by y sin y plus cos y plus x, right? Finally, cross multiply and you finally get the fact that y sin y plus cos y plus x times y dash equals 5, right? Sorry for coughing, my throat is actually question number 9. Question number 9 says that x plus y equals tan inverse y is a solution of, right? Is a solution of y square y dash plus y square plus 1 equals 0, right? So you basically have the fact that tan inverse y minus y equals x, right? Differentiating on both sides by d by dx, you basically get that 1 by 1 plus y square into y dash minus y dash equals 1, right? So y dash into 1 minus y square divided by 1 minus y 1 plus y square is basically equal to 1. So you basically have that y dash, this is minus y dash y square equals 1 plus y square, right? So therefore, y dash into y square plus y square plus 1 equals 0 is the required differential equation. And that is what this is, again, verified. So, right, yeah, again, this is basically the same as this. So this is also verified, right? So verified, I'm just writing a T for true, but it is the same thing, whatever. And finally, the 10th question, right? Y equals square root a square minus x squared as a solution to the equation x plus y dash equals 0, right? Two things. I can actually do this question in two methods, right? First of all, I can do in the normal method that we've been following for the first 9 questions. Or I can also do, do the derivation as how this came out, right? Instead of, going from here to here, I can go from here to here, right? I'll do both methods. First, your general method, right? The general method is that you basically see the highest order term here, that's 1. So you differentiate once, y dash is 1 by root of a square minus x square, 2 root, right? 1 by 2 root a square minus x square into minus 2x, right? Which is basically minus x divided by y. So y dash is equal to minus x, or x plus y dash equals 0. That's this verified, right? Or the second method, that is from here to here, right? And this basically only can only happen if x is between minus a and plus a, or y becomes complex and not real, and you won't have a circle, right? And for this to happen, y has to be non-zero over here. But yeah, the second method is to remember that y equals root of a square minus x square basically defines a circle, right? Or a semicircle. No, it defines a circle, right? No, it defines a semicircle in the positive half, right? So basically, y equals root of a square minus x square is this curve, right? This is my x equals minus a, this is x equals plus a. This curve is what is represented by y. Cool. So what you need to remember is that the equation of that curve is y square plus x square equals a square. Differentiating this, you get 2y y dash plus 2x equals 0, right? So goes of y dash plus x equals 0, right? And this becomes x squared equals, okay, y squared is a squared minus x squared, or y equals square root of a squared minus x, right? So you basically see that this and this are two different forms of the same expression, same curve, and so these both are equal, right? And so this has to be a solution of this differential equation because they represent the same thing, right? That's how you go about it, right? That takes care of question number 10, right? Question number 11 is there a number of arbitrary constants with general solution of differential equation of fourth order, right? Generally, the number of arbitrary constants for an n order expression, right? An nth order expression will have n arbitrary constants. Cool. Therefore, solution is D, that's 4, right? And here, the number of arbitrary constants, the particular solution of differential equation is always 0, right? You will not have arbitrary constants in a particular solution, never. Because by definition, a particular solution has no arbitrary constants, that's it. Well, now going to exercise 10.3. Before that, here, you deal with the formation of differential equation when the general solution is given, right? So here you verify, given the solution and the differential equation, that this differential equation has this equation as a solution, right? But here, what are given is this solution, and then you form a differential equation with this equation, right? So you have first you deal with this circle. Here the circle is at center 0, 0, but here the circle is having a different center, right? You have done coordinate geometry, then you know that this circle will have a center -1, 2 and a radius of whatever, radius of 1 minute, right? Pretty easy to check. If I'm not wrong, it's root of x square plus g square minus c. If it's x square plus y square plus 2fx plus 2gy plus c is equal to 0, something like that. Differentiating one, you get this equation, which is the differential equation, and then cross multiply and you linearize whatever, right? And finally, you'll notice that this differential equation is not a single circle, but it's a family of circles, and of which one member is given over here, right? When you differentiate it, you basically exclude this constant part. And so you basically remove the information pertaining to what the radius of the circle is, right? And so when you differentiate this equation and bring this circle's equation to a differential form, what you basically do is, instead of defining one circle, you will start defining all concentric circles with the center at the same place with non-constant radii, right? This is R1, This is R2, right? But they both have the same differential equation. That is this, right? That's what happens, right? I had to say that because many people forget this happens, right? Ooh, right. Same thing happens to lines, and same this basically is referred to as a family of curves, right? Because a line is also a curve. Do not forget. By curves, we mean every equation that can be represented on the XY plane, right? The order of a differential equation representing a family of curves is the same as the number of arbitrary constants present in the equation corresponding to the family of curves, right? So for example, if you wanted to find out the general equation for all circles lying in the plane, you will have you will have a differential equation of order 3, because there are 3 constants that determine what the circle is all about, right? The 2 constants are referring to the center and the 1 constant referring to its radius, right? So the order of the differential equation for all circles in the plane is 3, right? Similarly, you will have a differential equation of order 1 for family of curves y equals mx. Something like y equals a sin x plus b will have a differential equation of order 2, and something like this, the family of ellipses having center at the origin and foci on the x-axis, that is the major axis x, will be a differential equation again of order 2, right? The lesser number of constraints you have, the greater is the order of the differential equation. That is something that you have, right? Going to exercise number 9.3. This is it. I'll give this up. Question number 1, right? Instead of exercises 1 to 5, form a differential equation representing the family of curves by eliminating arbitrary constants a and b, right? First of all, here, first one, x by a plus y by b equals 1. Since you have 2 arbitrary constants a and b, this is going to be a differential equation of order 2, easy to see, right? And to differentiate, I'm basically bringing this in a form that's very easy to differentiate for me, and so it's easy to this x by a, right? So first of all, y dash is minus bx, right? Because it's y dash by b equals 0 minus right. So y is equal to b minus bx b by a into x, right? First of all, y dash equals minus b by a, y double dash is 0. So just now, since you have this equation where you can basically equate y double dash to 0, this is your equate equation over. And because you don't really need to substitute this b by a into an expression and find out what's the value of b, what's the value of a, etc., etc. You can just say that y double dash equals 0. And if you really have to integrate it out, basically get that y dash is equal to c from here, and then you'll get that y is equal to x, cx, wait, y is equal to cx plus b, right? And from which you get the fact that it's y by c equals x plus b by c, right? And you can basically say that this is equal to 1, right? And 1 by a minus 1 by a equals 1, right? And 1 by c equals 1 by b. Similar like this you can do, and you can basically find out the values of a, b, c, and d, and you can basically plug in this equation and you can get back this form, right? So this differential equation is what you need, y double dash equals 0, right? This is the back step to prove that this is the correct differential equation. This is out, okay, whatever it is, right? Question number 2, y squared equals a times b squared minus x squared, right? Again, a and b, 2 arbitrary constants, so it's an order of degree 2. It's an order 2 differential equation, right? So here, first of all, you do 2 by y dash equals a times minus 2x, right? And from here, you get the u32, right? So basically x, it's x plus y dash equals 0, right? From here, differentiate again to get a plus y dash squared plus y into y double dash, right? Since you have this a again, I'm basically bringing in this, bringing it to this side as minus a. So yeah, so you basically have the fact that putting this over here, I get y dash equals x times y dash squared plus y double dash, or xy y double dash plus x y dash squared minus y dash equals 0. And that is your required differential equation, right? To form this, basically what you do is you eliminate the two arbitrary constants however necessary, right? So you have xy d squared y by dx squared plus x into dy by dx the whole square minus y into dy by dx equals 0. That's a required equation, right? Number 3, y equals a e power 3x plus b e power minus 2x, right? First of all, y dash here is 3a e power 3x minus 2b e power minus 2x, and y double dash is 9a e power 3x minus plus 4b e power minus 2x, right? Now, what you do is you eliminate a and b step by step, right? First, you eliminate a. That is, you'll notice that y dash minus 3 times y gives you something like 3a minus 3a into e power 3x, that becomes 0. Minus 2b minus 3b, that's this is minus 5b e power minus 2x, right? And you'll notice that y double dash minus 9y gives you 4 minus 9, that's again minus 5b e power minus 2x, right? So you basically have the fact that y dash minus 3y equals y double dash minus 9y, or y double dash equals y dash plus 6y. That is a required differential equation, right? That is question number 3. Question number 4. Y equals e power 2x times a plus bx, right? Again, two arbitrary constants, order 2, right? First of all, what is y dash? It is 2a e power 2x plus e power 2x plus 2bx e power 2x, right? And y double dash, on the other hand, is 4a e power 2x plus 2b e power 2x plus 2b e power 2x plus 4bx e power 2x, right? This is basically 4a e power 2x plus 4b e power 2x plus 4bx e power 2x. That you can simplify as 4 times, it's 4 e power 2x times a plus b plus bx, right? Now you can see that this can be basically spread as 4 e power 2x times a plus bx plus 4b e power 2x, right? And this is basically 4y. And because a power 2x into a plus bx is 4y, right? But you have this term which is just dangling. You have to figure out a way to condense this to something regarding y double dash, y dash and y. So what you can do is basically see the equations of y dash and y, right? So if you do y dash minus 2y, what happens is y dash is e power 2x, it's 2 e power 2x into a plus b, it's a plus bx plus b e power 2x, right? So y dash minus 2y is basically b e power 2x, right? Because this is 2 times of this a e power 2x, and this is 2 times of this bx e power 2x, right? And you have this dangling out. So y dash minus 2y is this. So you have this to be 4y dash minus 8y, right? So finally, you have the fact that y double dash equals 4y dash minus 4y as your answer. Question number 5. Y equals e power x into a cos x plus b sin x. Right. Here, first of all, again, we have to do with two differentials. First one is y dash is e power x into a cos x plus b sin x plus e power x into b cos x minus a sin x. Right. This is basically y plus e power x into b cos x minus a sin x. Right? Y double dash on the other hand is basically y dash plus e power x into b cos x minus a sin x minus, wait, it's plus e power x times minus a cos x minus b sin x, right? Which is basically y dash plus this term minus e power x into a cos x plus b sin x. That is this, that is y, right? And this term is basically this term, which is y dash minus y. So I can write here is y dash minus y, right? Therefore, you have the differential equation y double dash equals 2y dash minus 2y. That's the required differential equation, right? Takes care of the first 5 questions. Then question number 6. Form the differential equation of the family of circles touching the y-axis at origin, right? Differential equation of the family of circles touching the y-axis at the origin. So basically, the circles form like this, right? Everything touches the y-axis at the origin, and it's not limited to one side. It's limited. It holds true for both sides, right? I'm not drawing bigger circles over here because that is basically a waste of time for me. But they are basically infinite circles, right? And they do not have a fixed center. They are all having different centers, different radii. The only thing that they have in common is that they touch the origin and they touch the y-axis, right? The origin is the point of tangency for every circle with the y-axis, right? So basically, 2 things we can figure out. One is that their centers, every one of their centers is of the form sum x comma 0, right? And you have the fact that the distance of each of their centers from the origin, that's r, that's the radius, right? And that is the distance between the center and the origin. So basically, if the center C is x comma 0, then the radius is x. These are 2 facts we can bring out from the given data. And so we can basically say that the equation of the circle then becomes x minus r the whole squared plus y squared equals r squared, right? Because center is r comma 0 and the radius is r, right? Here I've used x, but make it x1 in that sense. So I'll just I'll just avoid confusion, right? Is x minus x1 the whole square plus y squared equals x1 the whole square, right? And here x1 is a point. It's not d by dx of x. Please don't make that mistake, right? So this is the equation of a circle. To bring this into a differential form, again, know that there is only one arbitrary constant, that's x1, right? And not two. So make it standard, right? So it's x squared plus x1 squared plus y squared minus 2x x1 equals x1 squared, right? x1 square cancels out and you're left with x squared plus y squared minus 2x x1 equals 0, right? Differentiate to get our 2x plus 2y dash minus 2x1 equals 0, right? That means I'll bring this to the other side. 2x1 equals 2x plus 2y dash, right? Substituting this in this, we get x squared plus y squared minus 2 times x into 2x plus 2y dash equals 0. That means x squared minus 4x squared plus y squared equals 4xy dash, right? And so y squared minus 3x squared equals 4xy dash is very, very question. Wait a minute. Right. I'm sorry. This is 2x1, which we are substituting over here. So this 2 will not come here. It's 2, it's again 2. And so we have 8. This is basically y square minus x square. And this is 2x y dash. Right? And that is your required differential equation. Y square minus x square is 2 times xy into y dash. Right? I'll just write this down further because so it's basically y square minus x square equals 2xy times y dash. That's question number 6. Question number 7. Form the differential equation of family of parabolae having vertex at origin and axis along positive y-axis. So basically, what they want is the origin is a family of parabolae having the vertex at origin and axis along the positive y-axis. Since the axis has to pass through the vertex, this basically means that the axis of every parabola is the y-axis itself, right? Because it has to be along the y-axis and it has to also pass through the origin, that is the y-axis, right? And so you have this kind of a family which has different foci, right? But which has the same axis and the same vertex. So what happens is we can use the vertex axis formula for a parabola that goes by what? Y square equals 4ax, right? This is the vertex axis formula where y is your, right? This is a formula where this defines your focal length and this being your the major axis, right? This is an x major axis type of parabola. And for y major axis parabola, what you do is this becomes y equals, right? It's 4ay equals x squared. 4ay, right? This is the standard equation for curves of this form, right? So this family of curves, basically, this family of curves is represented by this equation x square equals 4ay. Not this, but this. Okay. So from here, differentiating y once, you basically get 4ay dash equals 2x, which means that y dash is x by 2a, right? So from here, you basically get that y is equal to x squared by 4a, which is equal to x by 2 into x by 2a, which is equal to xy dash divided by 2. So basically, y dash is equal to 2y by x. That is the required differential equation in any different form, right? Or you can say that xy dash equals to whatever, but I usually like this kind of a representation where you only have a differential term on one side and the constant terms on the other, and the non-differential terms on the other, right? And so this is basically the required differential equation. You can write this in any form, right? Xy dash equals to y, or xy dash by y equals to, or xy dash minus 2y equals 0. Whatever form you write, that's correct, right? Nobody cares about that. It's just that you need to get this form perfectly. Cool. Question number 8. Form the differential equation of the family of ellipses having the foci on y-axis and the center at origin. Right? Again, simplistic. Right? Since you have a family of ellipses with the foci on the y-axis and this is the origin, so basically you have an ellipse over here, you'll have an ellipse over here, you'll have an ellipse over here, and then you'll have an ellipse over here, and then you'll have an ellipse over here, etc., 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 so on and so forth about everything. Right? Everything will be concentrated because everything has a center at origin. And since everything has a focus on the y-axis, these are all y-axis featured ellipses. Right? You won't have an ellipse of this form. You won't have this kind of an ellipse is forbidden. Right? These ellipses are what are what that's a family. Right? And these ellipses of a normal ellipse is of the form of x squared by a squared plus y squared by b squared equals 1. Right? Centered at the origin with the x-axis and the y-axis measure. Right? And if b squared is greater than a squared, then it's a y-axis measure ellipse. Cool. So you have the constraint that b is greater than a, first of all. Since b and a are positive integers, no need to worry about minus b being less than x. B is greater than, right? And then you basically have that there are two arbitrary constants only defined by this relation, which does not really give that much of constraint. And so you have to differentiate it twice, right? First time you get y dash by b squared plus x dash plus x by a squared, right, equals 0. And the second time you basically get y dash the whole square plus y double dash divided by b squared plus 1 by a squared equals 0. Right? You basically get that y dash the whole square plus y double dash equals minus b squared by a squared. And from here, you get that y dash equals minus b squared by a squared times x. So basically, substituting this in this, you get the fact that y dash equals x times y dash squared plus y into y double dash, which is basically xy y double dash plus xy dash squared minus y dash equals 0. Right? You'll notice that it's this kind of an equation is eerily similar to what we got in question number 2. Right? Because I think in question number 2, what we got is, if I'm not wrong, I'll just go up. Right? This is question number 8. And in question number 2, 5, 4, 3, 2, right? X by y double dash plus x y dash square minus y dash equals 0. Right? It is the same equation. Right? And you may think why exactly is the same, because we have used different equations, right? There we have y squared equals a into b squared minus x squared, while here we have x squared by a squared plus y squared by b squared equals 1. But they get the same differential equation. Why? It's because both of these represent the same kind of ellipses, right? What happens here is that if you bring it to an ellipse standard form, right? So again, divided by b square, you get y squared by ab square plus x squared by b square equals 1. which is a form of an ellipse, right? This is basically an ellipse. So this and this are the same family and so have the same differential equation, right? That's question number 8. Then question number 9. Differential equation of the family of hyperbolae having foci on x-axis and center at the origin. So basically all these kinds of hyperbolae which have the center at the origin and foci on the x-axis, right? Everybody knows that these kinds of hyperbolae have the formula x square by a square minus y square by b square equals 1, right? Standard form. And so there are no constraints, right? So basically, so you have two arbitrary constants, right? And so you need a second order differential equation. Again, differentiated twice, you'll get x divided by a squared minus y dash by b squared equals 0, firstly. And then not even x, it's 1 by a squared minus y dash the whole square plus y double dash by b squared equals 0, right? And so you basically get the fact that y dash into y dash plus y double dash equals b squared by a squared, right? And from here you get that y dash is equal to b squared by a squared into x squared, right, into x, right? And so from here, substitute this in this, you basically get the fact that y dash equals y dash the whole is equal to x y dash the whole square plus xy y double dash. Now, you again notice that this family is the same as the family of ellipses, right? And I leave it to you to figure whites. Why is that case? And now there will be a burning question. How exactly do you determine, if you have to solve this equation, how exactly do you determine that you have to form a hyperbola, that you have to form an ellipse of this form or of this form, right? Basically, that depends on what the initial value or what the parameter you're given pertains to. If you're given a parameter that pertains to hyperbola, then you have to form this kind of hyperbola from this equation, right? If you're given a parameter that pertains to an ellipse, then you have to form this kind of an ellipse with the focus on the x-axis or the y-axis, right? However it's given, right? Depends on your initial value, what kind of an equation you form from this kind of from solving this kind of equation, right? That is how you determine what you form. The family of ellipses includes the family of hyperbola. Question number 10. Form the differential equation of the family of circles having center on y-axis and radius 3. Right? So basically here what you have to do is that center on y-axis and radius 3. So basically you have these kinds of circles, overlapping circles, each having a center on the y-axis, right? Excuse my excuse this being skewed, but consider that it has a center on the y-axis, right? And every circle has a radius to the right? So for these circles, you have to find the family formula. Basically, since the centers lie on the y-axis, center x is 0 and center y is whatever, right? Y minus a whole square equals, right? Because the radius is fixed, right? And the center is basically 0, a, right? A can be whatever. This gives me an equation of the form x squared plus y squared minus 2ay plus a squared equals 9, right? This means since you have only one arbitrary constant, then you need a 1 degree equation. It's a single order, a first order differential, right? So differentiate once, you get the fact that y dash plus x is 2y dash plus 2x minus 2a y dash, right? And so you basically get the fact that 2a is equal to 2y plus 2x divided by y dash. Or the fact that answer is basically y plus x by y dash, right? And so you basically substitute this in the above equation, right? You substitute this in this equation, because if you do this in this equation, then you have to square this out, and that is a bit of headache, right? So you basically do x5. Now, that's simple, right? X square plus y minus a the whole square, right? Y and a is y plus x by y dash. So you basically do y minus y minus x by y dash the whole square equals 9. So finally you get x squared plus x squared by y dash squared equals 9, or basically say that x squared y dash squared plus x squared minus 9y dash squared is, and that is a required expression, right? Finally, question number 11 and 12. 11. Which of the following differential equations has y equals c1 e power x plus c2 e power minus x as children? Right. Simple. Here you have the equation y equals c1 e power x plus c2 e power minus x. Right. Say that you can say that it's a second order differential equation because there are two arbitrary constants. Yeah, ideals. Y dash is basically c1 e power x minus c2 e power minus x. Y double dash is c1 e power x plus c2 e power minus x, which is basically y. So y double dash equals y is your required equation, right? If you had, instead of c1 e power x plus c2 e power minus x, if you had something like c1 sin x plus c2 cos x, right? Then you will have this y equals of course, right? This will give you y double dash equals minus y as a differential equation. You can write out, right? Because one differentiate once, you get a cos x minus b sin x, and then differentiate twice, you get minus a sin x minus b cos x, which is basically y, which is basically minus. So you will arrive at the differential equation y double dash equals minus. This form is for this, right? Answer for this, I'm going to question number 10. The following differential equation has y equals x as one of its particular solutions. Here, since it's a particular solution, you can't really use any trick or something, but you'll have to solve it out because you can't derive what the differential equation is from a particular solution, right? So, first off, y equals x means that y dash is 1, y double dash, and further is 0. Remember that, right? If this is the case, then first equation 0 minus x square y plus xy is not equal to x, right? So A is wrong. Right? B 0. This is x y. This is x. X plus xy equals x. Second wrong. C, this is 0. This is x square y. This is x square. This is if this is a minus and this is a plus, again this is x square minus xy, right? This is 0. This is correct because y is x, and so this also x square, right? Plus x divided by dx plus xy is 0. This is wrong because it's x square, but this is x. Right? X plus x square cannot be 0. So the answer should be C. Even though there's a print loss. Right. Cool. That finishes 9.3. then proceed into 9.4, right? In 9.4, you would start with the methods of solving first order first degree differential equations. That is the variable separable format, where you separate each of the variables like hy and gx, and then you do dy by hy into this dy by hy equals gx and dx and integrate both, right? Finally, you get this kind of a solution in this format, right? You have the different examples. Please, guys, see the examples because they are very important, and there are some very good questions and some very good points you'll note when you look at this. Okay. This notation, this note is just for is just a history where you are given what this notation given by dx is important for, right? It was introduced by Leibniz, and it's used in many calculation and formal transformations where we deal with symbols divided by dx exactly as if they were ordinary numbers, because they are very infinitesimal quantities, but they also are real and not really, they are not something like an infinity which is not quantifiable, right? They are also ordinary numbers, but they are very infinitesimal. They are not exactly x and y, but they are separate entities, and you can treat them as separate variables. Going to exercise number. For each of the differential equations in exercises 1 to 10, 5 to 7. Okay. You have what? 23 questions. So we're dealing with the variable separable method, right? First one, dy by dx equals 1 minus cos x by 1 plus cos x. First things first, can you simplify this? Right? And just take think, and then I'll do it. But I'll do it. Right? Okay. So notice that cos x can be written as cos of 2 into x by 2. Right? And cos 2x is basically 2 cos square x minus 1. This is equal to 1 minus 2 sin square x by 2. Equivalent forms, but that's important. That can be important, right? You can basically represent this as sin squared x by 2 divided by cos squared x by 2, which is tan squared x by 2, which is secant squared x by 2 minus 1, right? dy is equal to secant squared x by 2 dx minus 1 dx, right? Integrating unbound integration on both sides. This is basically x. This is tan x by 2 into 2. This is basically tan of x by 2 divided by half, which is 2 tan x by 2, right? And this is y. So you basically get y equals 2 tan x by 2 minus x plus c. Perfect. Now, what happens if we don't do this? What happens if we don't use the half angle formula to actually simplify this? You'll notice that you can't really integrate 1 minus cos x by 1 plus cos x directly, right? You'll have to simplify this somehow, and the easiest way to simplify this is by using the half angle formula, right? What you else can do is rationalize this and basically get 1 minus cos square over here, but do 1 minus cos x the whole square, right? So I basically get in the denominator something like sin squared x, and you will have in the numerator something like 1 minus 2 cos x plus cos squared x, right? Which is very difficult to integrate again. So you basically, so you can basically do this is the easiest way, and then get this as the answer, right? Instead of going through this form and then marking up for cos. This is basically called, this is cosecant square x, but then you'll have this 2 cosecant x cot x left. It's also easy to integrate, but then you'll have a bigger formula to actually state, and then you'll give the correct answer again, but you just have to work a lot, right? And you'll have to think a lot. Whatever. Yeah. Question number 1. Question number 2. Y dash equals square root of 4 minus y squared, where y is between minus 12 plus 2. I'm not writing down the conditions, but remember that this condition is there and it's very important, right? Because sometimes when you take your integrations, you will deal with bounded integrations, and then these boundary conditions become very, very, very important. Cool. Right. So you have this, right? Which means that dy by square root of 4 minus y squared equals dx directly, right? Because I can't separate something under, and doing integration with dy the whole square is stupid, right? This you can see is like is almost a standard formula where it's a root of a square minus y square, correct? And so taking your unbounded integral on both sides, on this side you have x, on this side you'll have sine inverse of y by 2, correct? Therefore, y is equal to 2 sine, this is a representation, right? Very simple. Third is y dash plus y equals 1, or y dash, this can be rewritten as y dash equals 1 minus y, right? This means dy by 1 minus y equals dx. Taking an integral on both sides again, you basically see that ln of 1 minus y equals x plus c, right? Therefore, you have 1 minus y equals e power minus x into c1, right? Because if this is minus c, then you can basically write this as e power c, which is again a constant, which is c1, right? And basically condensing that. And so you have y equals 1 minus c power minus x. That is a general solution, right? Or instead of c, you can basically write this as 1 minus a power minus x, whatever. Right? Nobody actually cares. Then question number 4. Secant square x tan y dx plus secant square y tan x dy, right? In the variable separable form, what you have to do is separate all x terms on one side, separate all y terms on the other, right? So what you're going to do here is, first of all, secant square x tan y dx equals minus secant square y tan x dy, right? And then bring this tan y over here, take this tan x over there, and voila, you have your necessary. Well, now you think of your integration. Notice that you have secant square x dx over here, and you have secant square y dy over here, right? What is the differentiation of tan x with secant square x, right? So here, take tan x equals t and tan y, right? So this means that secant square x dx is this is basically dt, and this is basically du, correct? And so you are basically left with the integral dt by t equals minus integral du by u, which is the fact that ln mod t is equal to minus ln mod u plus c, which basically states that ln of tan x plus ln of tan y is a constant c, right? Which means that tan x tan y is a constant c, right? Because if you remove this log, what happens is this becomes e power c, but e power constant is also a constant, right? So basically you can write this as tan x tan y equals constant. That is the final expression. This is the general solution for secant square x tan y dx, the secant square by tan x to y, right? Now 5 e power x plus e power minus x dy equals e power x minus e power minus x dx, right? Bring this to the other side because there is no dy term and these are all dx x terms, right? Let t equals e power x plus e power minus x. Then dt is basically e power x minus e power minus x times dx. Yes or no? Therefore, this equation can be written as dy equals dt divided by t. Integrate on both sides. This basically gets y equals t plus c, which is y equals e power x plus e power minus x plus c. There is option ln mod t. Yeah, forgot. This is not just dt, this dt by t, right? And so you will have a ln mod ex plus e power minus x plus c, right? Ln is a ln, that's natural log. That's question number 5. Question number 6. 6 is y dash equals 1 plus x squared into 1 plus y squared, right? Here it's dy by 1 plus y squared equals 1 plus x squared times dx. This is basically tan inverse y equals, this is x plus x cubed by 3 plus c, right? Taking into account both sides. These are standard integrals, right? Everybody should know this. Nobody should be confused. Yeah, this is solution. This is direct, right? So I'm not spending much time on this. I'm just directly going to the steps, giving some steps wherever necessary, and then write the answer. Question number 7. It's y ln y dx equals x dy, right? And so you have x over here, y ln y over here. I rewritten as dx by x, integral dy by y ln y, right? This is basically ln mod x, easy to see. Here, take t equals ln y. Then dt is equal to 1 by dx, right? Wait, this is dy, 1 by dy, right? And so this can be basically written as integral of dt divided by t again, which is ln mod ln y, right? Because it's ln mod t, which is ln mod t is ln y, so it's ln mod ln y, right? Therefore, basically have this in the solution ln mod x equals ln mod ln y plus c. This is basically ln mod of x by ln y equals constant, which means that x is equal to some other constant into ln y. Because remembering this ln makes the e power a constant, which is also a constant. This basically reduces down to y equals e power e dash x. Or you can basically represent this as y equals e power ax for some. That's what this is. Right? That's question number 7, right? Going to question number 8. For question number 8, you have x power 5 divided by dx equals minus 5 power 5, right? Again, cross multiplying, we're going to skip that first step and directly write this as dy by y power 5 equals minus dx by x. So basically, minus what? The integral of x power n dx is x power n plus 1 by n plus 1, right? So it's basically minus 1 by 4y power 4 equals minus of minus 1 by 4 x power 4 plus minus 1 is cancelled. So you're basically left with 1 by y power 4 plus 1 by x power 4 is equal to constant, right? Y dash equals sine inverse x. Okay. Give me a second. Oh, question number 9. Y dash equals sine inverse x. Here, again, basically the same thing that we've been doing so far, right? dy equals sine inverse x times dx, right? I have to integrate this. How do you integrate sine inverse x dx? Oh. Did anybody have any idea? What you basically do is you apply the UV rule of integration over here, right? So y equals integral of sine inverse x plus c sine inverse x dx, right? Which is the integral of 1 times sine inverse x dx, right? It's sine inverse x times 1. This is equal to sine inverse x into x minus integral of dx x dx divided by root over 1 minus x squared, right? This is integration by parts. You should all know this formula, right? The UV rule of integration or integration by parts, whatever you want to call it, right? You basically do it's u integral b minus integral of different du by du into integral of v dx, right? So that's the formula I've used here. Is x into sine inverse x minus integral of x dx divided by 1 minus x squared. And here, if you can see, taking this, what is under this root, that is 1 minus x squared as t, we basically get dt is equal to minus 2x dx, right? And so making this, so if you just take minus integral of x dx by root over 1 minus x squared, what you'll see is you can basically transform this into half of, this is plus, right? Because the minus has been used over here. It's half of dt divided by root t, which is basically half into something like square root t divided by half, right? Because it's n plus 1 by n plus 1. Right? Cancels, which is basically root. So the integral of this is root of t, that's root of 1 minus x squared, right? So therefore, this basically gives me x sine inverse x plus square root 1 minus x squared plus c. That's y, right? Yeah. Y is equal to x sine inverse x plus root of 1 minus x squared plus c. Finally, question number 10. E power x tan y dx plus 1 minus e power minus x, 1 minus e power x secant square y dy equals 0. Again, you have to use the variable separable method, right? Or you have to be a little clever. And you can, I can actually do this question in 2 ways, right? I'll first show you the variable separable method. First, as usual, instead of this, and basically write an equal to over here, here a minus, and is equal to, right? And then as usual, I'll just cross multiply. Exj divided by e power x minus 1 is equal to secant squared y dy by tan y, right? This is basically if this this you represent by t, this whole thing becomes dt. Again, if you represent this as u, then this whole thing becomes du. Therefore, this is basically equal to integral of dt by t equals integral of du by u, which is basically ln mod t equals ln mod u plus c, which is basically ln mod e power x minus 1 equals ln mod tan y plus c. This can be rewritten as e power x minus 1 equals c1 tan y, right? That is how you can write this equation. Oh. Or you can be a little cleverer. What you can do? This is method 2, right? What you can do? First of all, notice that this is dx. That means that this term has been you have this term after differentiation to x, right? You haven't differentiated the y term, but you have only differentiated the x term, right? So in your final answer, you will have a y term over here, right? Again, over here, you have not differentiated the x term, but you have only differentiated the y term, right? And since the differential of the y term is secant square by dy, you can see that your y term is actually tan y, right? That is something that supports this. But the problem arises when you have this is 1 minus e power x, but you have e power x dx, right? That is a problem because differential of 1 minus e power x is minus e power x, but here is plus, right? So what do? You basically take this to the other side, right? And you basically see that this is tan y, and on the other side, since you have e power x minus 1, but here it's a dx and there is dy, so it's basically an equal to, and then you put here e power x minus 1, and then you multiply a constant over here, right? So your final answer becomes c into e power x minus 1 equals tan y. This is not something you can do into both, but it's something that you can do in JEE Mains and advanced, because there you have to save time, right? And so this is a shortcut. You can't use this in every situation, but this is something like what you do when you deal with exact differentials, which you not use in NCERT, you can use it or NEET or whatever exam. This is a very shortcut method that you can use to solve this kind of differential equation, right? For either the differential equations, find a particular solution satisfying the given condition. Question number 11, right? It's x cubed plus x squared plus x plus 1 y dash equals 2x squared, given that y equals 1 when x is 0. Now, what we do here is that we solve this differential equation through the given formula, and then we substitute this value of y and x, right? And then you'll get a particular solution, a particular curve that satisfies this differential equation. That is the funda behind the question. All right. So in the doing a normal variable separable method, where it is dy equals 2x squared plus x dx divided by x cubed plus x squared plus x plus 4. And so you will basically write this as 2x squared plus x into dx divided by x square plus 1 into x plus 1, right? This is split as this is a by, right, that is a by x plus 1 plus dx plus c divided by x squared plus 1. In normal integration to partial fractions, I hope that whoever sees this video knows that this is the way you split for partial fractions when you have x squared plus 1 into x plus 1 in the denominator, right? It's not a square, right? And basically just going through the motions where if you cross multiply this is ax squared plus a plus bx squared plus c plus b into x plus c in the numerator divided by the whole denominator. So you basically have the fact that a plus b is 1, b plus c is also 1, a plus b is 2, b plus c is 1, a plus c is 0, right? And so you have that a is equal to minus c. So b plus c is 1, b minus c is 2, b is 1.5, c is minus 0.5, right? And a is plus 0.5. So you basically have y equals half integral 1 by x plus 1 plus half integral 3x plus it's 3x minus 1, right? X minus 1 divided by x square plus 1. Give me a moment, just stop. So this is basically half ln mod x plus 1, and this is half of 3x by x square plus 1 dx minus half integral dx by x square plus 1. This is basically half of tan inverse x, right? So I don't need to worry about this further. And of course, this is plus. The only problem is this. Now, what you can do is that you can basically make this 2, right? For that, you need to basically take this 3 out and multiply and divide by 2. 2x dx by 1 plus x squared. So this is basically 3 by 4 ln mod, right? Therefore, y equals half ln mod 1 plus x plus 3 by 4 ln mod 1 plus x squared plus minus half tan inverse x plus c. This whole thing is an answer, right? And now we have to find, a particular solution, right? Y is 1, then x is 0. What happens when x is 0? This is 0. So this ln 1, ln 1 is 0. This is 0. This again ln 1, ln 1 is 0. Tan inverse 0 is also 0. So basically you have y equals c and x equals 0, which means that c is 1, right? Because when x is 0, y is 1. And if y is 1, c is 1. Therefore, particular solution is y equals half ln mod 1 plus x plus 3 by 4 ln mod 1 plus x squared minus half tan inverse x plus 1. This is right. So, yeah, question number 1. Right? X times x square plus 1 dy equals x. And y is 0, then x is 2. Same as before, first find the general solution. That is dy equals variables if plug in. Dy is dx by x into x squared plus 1. Right? Same as before, use partial fractions. You'll get something like y equals. I'm not dealing with the partial fraction again. Alright. So I'm just skipping that. And directly you'll get y equals something like, directly you get something like y equals half log mod x plus 1 plus half log mod x minus 1 minus half minus not half minus log mod x plus c. That'll be your answer, right? Because this will split itself as dx by x plus half dx by x minus 1 plus half dx by x plus 1. I'm not wrong, right? X minus. So basically this will give you what this will give you x by x squared minus 1. And then if you multiply, it will be minus plus x squared. So this 1 by x and x squared plus 1. Yeah. So this will be the partial fraction decomposition that we get from this, right? And so this will be our formula for y. This will be the general solution, general, right? When y is when x is 2, y is 0. When x is 2 over here, what you basically get is this will be 0, right? This will be minus log mod 2. This will be half of log 3, right? So c is basically log 2 minus half of log 3. Therefore, the particular solution is y equals half log mod x plus 1 plus half log mod x minus 1 minus log mod x plus log 2 minus half log 3. Right? Very big, but just don't make a mistake while writing out the whole thing, because sometimes what happens is you copy things wrong. And if you copy things wrong, your answer is correct. That's true. Right? And then going to 13. 13, for 13, what you do is, again, y is 2 when x is 0, and this cos of dy by dx equals a, you take this term to the other side, right? And so basically have the equation y dash equals a times cos inverse, y dash is cos inverse a, right? That's the equation over here, right? And you see that a is belonging to R, a is a constant, right? It's not some kind of a dependent or an independent variable, a is a constant. So cos inverse a is also a constant, right? Therefore, this equation is basically y dash equals constant. That is dy equals c times dx, or y equals cx plus d, right? Where c is basically cos inverse a. And remember that a is a constant and a is not a variable, right? So the only arbitrary constant over here, the only thing that can vary is this d, right? This is the only thing that can influence the the order of the differential equation, and not this also, because this is not an arbitrary constant. This is a given constant, right? This is a belonging to R being given constant. Cool. And so you have the fact that the general solution is y equals cos inverse a times x plus b, right? And since y equals 2 when x is 0, right, this d is basically 2. So this is a particular solution. Y equals finally 14, right? Y dash equals y tan x. Same old, dy by dy, dy by y equals tan x dx, right? How you integrate tan x? Again, is by parts. And so you have ln mod y equals, that's what? Tan x into 1, it's tan x squared times standard cost. Yeah, whatever. So you basically get this is ln mod secant x plus e. Therefore, you basically write it as y equals c1 secant x, right? Y equals some constant times secant x. Because if you know this is basically y equals e per c. This is if you bring this inside, is basically e per c into secant x, and e per c is also another constant. Same way, right? And then since you have y equals 1 when x is 0, and when x is 0, secant x is 1. So c1 is 1, and so you can basically know the c1. And this is a particular solution. This is the solution. Y equals 0. Right? Now 15. Find the equation of a curve passing through the point 0, 0, and whose differential equation is y dash equals e power x sin x. Right? Y dash equals e power x into sin x. This means that dy equals e power x into sin x dx. This means that y is equal to e power x, but e power x sin x is you integrate e power x sin x by parts, and you get the formula as I think it is what? It's e power x sin x, and it's e power x cos x by 2. Not wrong, right? Yeah. So therefore, when you integrate this, you get y equals e power x sin x by 2 minus e power x cos x by 2 plus c. Right. Since you have the fact that it's passing through the point 0, 0, this equation should start as 0, 0. Right. And so you have 0 equals this, this is 0, this is 1, this is minus half, plus c being 0. And so c is minus half. Therefore, y equals e power x by 2 into sin x minus cos x minus half, right? Minus half plus half, plus half, right? Or 2y is equal to e power x and the sin x minus cos x plus 1, or 2y minus 1 equals e power x and sin x plus cos x, whatever, right? Whatever form this equation takes, this is basically the equal form of the curve that passes through the point 0, 0. And the differential equation is y dash equals e power x and x. Right. Question number 16 then. For the differential equation, what is this? For the differential equation, xy dy by dx equals x plus 2 into y plus 2. Right? What we can do here is I can separate y dy by y plus 2 equals x plus 2 dx by x. Right? So then, like, partial fractions is something what we can do here. This is basically 1 minus 2 dy by y plus 2. Right? Equaling, but this is dy minus 2 dy by y plus 2. Right? Equaling 1 plus 2 by x dx. Right? Integrating on both sides, this separates out to y minus 2 ln of y plus 2 in mod equaling x plus 2 ln mod x plus c. Right? This is a required curve. Right? I don't care about whatever similar form it takes. This may curve. And it passes through 1 comma minus 1. Therefore, for x 1, if x is 1, then this is 1 plus 2 into 0, that's 1. and 1 plus c is basically equal to this minus 1. So this minus 1 minus 2 ln 1. So this is minus 1, right? So c is basically minus 2. Therefore, the curve is y minus 2 ln mod y plus 2 equaling x plus 2 ln mod x minus 2. Or you can basically say that y minus x plus 2 is equal to ln mod or ln of x into y plus 2 the whole square, right? This works. This is pretty elegant and this is pretty simple also. That's it. Going to question number 70, right? Find the equation of a curve passing through 0, minus 2, given that at any point x, y in the curve, the product of the slope of its tangent, the slope of the tangent to a curve at any point is dy by dx, and the y coordinate of the point into y is equal to x coordinate of the point, right? So y dy is equal to x dx. Y squared equals x squared plus c, right? Because this is elementary integration. Since this passes through 0, minus 2, we have the fact that c is 4. And so you have the hyperbola y squared minus x squared equals 4, right? Now, question number 18. At any point x square of a curve, slope of tangent, the slope of the tangent dy by dx is twice the slope of the line segment joining the point of contact to the point minus 4, minus 3. 2 times the slope of the line segment joining point of contact, that is xy, to minus 4, minus 3. So this is basically 2 into y plus 3 divided by x plus 4. Find the equation of the curve given that it passes through minus 2, 1. Cool. That is simple again, right? This is basically dy by y plus 3 equals 2 dx by x plus 4. Again, very elementary. It's ln mod y plus 3 equaling 2 ln mod x plus 4 plus c, right? Which is basically y plus 3 equaling c into x plus 4 the whole square, right? Since it passes through minus 2, 1, right? What happens is you put here minus 2 and then this is 4c. If you put here 1, that's 4. 4c is 4, so c is 1. Therefore, c is equal to 1. And then y plus 3 equals x plus 4 the whole square. That is the required curve. That's the required parabola, right? Here, two things. First of all, this is again elementary integration. I'm not really explaining this step, right? And from here, you remove the ln, you put e power everywhere. This is basically y plus 3. This is x plus 4 the whole squared. And since this is e power something plus something, that's e power something, that's constant into this x plus 4 the whole square, right? So from here you basically do substitute minus 2, 1, and then you will notice that 4c equals 4, you get c equals 1. Well, from here you substitute, basically get the equation y plus 3 equals x plus 4 the whole square. That's the equation of the parabola that's needed, right? Question number 19. The volume of the spherical balloon being inflated changes at a constant rate. So if V is the volume, right, dV by dt, because rate is always taken with respect to time. So dV by dt is a constant, right? If initially this radius is 3 units at 0, if initially the radius is 3 units at 0, right? All pairs are t, x, t, b. It's t, r, right? 0, 3 moves down to 3,6. Okay. So find the radius of the balloon after t seconds. So you have the fact that dV by dt is constant, right? And volume is 4 by 3 pi r cube. Therefore, dV by dt is basically 4 by 3 pi r square into 3r squared dr by dt, which is basically 4 pi r square dr by dt, right? And this is a constant. So basically, dr by dt is equal to some other constant C1 divided by r square, right? And so you have the fact that if I just bring this r square over here, this dt over here, right, you have the fact that r cubed by 3 is ct for some c, right? In this 3 can get absorbed into this constant. So r cube is basically equal to ct. That is the metric that's used here, right? Initially, its radius is 0.3. For t equals 0, 8. So it's the ct plus t. I'm sorry, right? Integrating on both sides, you have r cube by 3 equals ct, right? And 3 becomes absorbed into this constant, these constants, both these constants, right? Nobody cares about the constant exactly because we are anyway going to find out the constant after this. So any constants you have here, you can get absorbed into these two arbitrary constants. Nobody cares, right? So you have first of all substitute 0,3 over here. You will notice that 27 is equal to 0 plus t, or t equals 27, right? First of all, and then you substitute 3,6, right? You'll notice that 216 is equal to 3 times c plus 27, right? This goes 9 times, this here goes 72 times, and 9 from here is 6. So c is equal to 6. Therefore, you have r cubed is 63 times t plus 27, or the radius of the balloon is the cube root of 63t plus 24. That is the answer, right? Then going to question number 20. In a bank, principal increases continuously at the rate of r% per year. All right. Find the value of r if 100 rupees 100 doubles itself in 10 years. Cool. So let P be the principal. If P is the principal amount, then you have the fact that dV by dt is equal to r by 100, right? Right. It's r by 100 times P. So you basically have the fact that ln mod P is equal to RT by 100 plus C. Cool. So you have, again, you have two data points over here. At t equals 0, you have rupees 100. And at t equals 10, you have rupees 200, right? Two data points. So using the first data point, at t equals 0, you have a principal of 100. You get the fact that ln of 100 is equal to C, right? And using the second data point now, and substituting the value of C, of course, you get the fact that ln of 200 is equal to 10R by 100 plus ln of 100. Okay. And this means that this is basically R by 10 equals ln of 200 divided by 100, right? Because ln a minus ln b is equal to ln of a by b, right? Which is ln2, please have given the value to be 0.693. 0.6931. Therefore, R equals this into 10, that's 6.931%, right? R percent is 6.9. Right. Question number 21. In a bank, principal increases continuously at the rate of 5% per year. So basically, dp by dt is equal to P by 20. An amount of 1,000 is deposited with this bank. How much will it be worth after 10 years? And they're given that our root E is 1.648, right? So basically from here, again, solving the same differential equation as before, you get it as a normal P is T by 20, right? So P is basically equal to is plus C. It is P is basically equal to E power C into E power T by 20. Sorry for that, right? So you have this equation which controls the amount and which relates the amount and the time it's in the bank. Right. At t equals 0, you have an amount of 1,000 rupees. So basically, 1,000 is equal to C. After 10 years, P is equal to 1,000 E power 10 by 20. This is equal to 1,000 E power half. This is equal to 1,000 into 1.648. That's rupees 1648. Right? Question number 22. Right? Because they have finished 21. Right. In a culture, the bacteria count is 1 lakh. The number increased by 10% in 2 hours. In how many hours will the count reach 200,000 if the rate of growth of bacteria is proportional to the number present? So basically, they're given that dN by dt is equal to C times N. It is proportional to the number present. So basically, you have the fact that at 0, the number is 100,000. In 2 hours, the number increased by 10%. That is 1,10,000, right? And they're asking if the data point is t, 2 lakhs, they're asking what is t. Here, what we can do is basically the same as before, right? dn by n is equal to c. So n is equal to c e power t. Wait a minute. N c when d e power ct. Then you have two variables, right? If this is the case, at time t equals 0, this is 1, and so at t equals 0, what happens is you get 1 lakh equals t into 1, right? So d is equal to 1 lakh, right? At t equals 2 hours, of course, t is always an hours. D is 1 lakh into e power 2c. E power 2c is equal to 1,10,000. So you basically have e power 2c is equal to 11 by 10, right? And e power c is equal to square root of 11 by 10. Finally, you have 200,000 is equal to 100,000 e power ct. Right? It is basically, so we have the fact that ln 2 is equal to t root of 11 by 10, which means that t is basically equal to square root 10 by 11 into ln 2, right? Which is, wait, no. Wait. I'm sorry. So I can't say this is, right? So this is 2 equals e power ct, and we have e power c equals root of 11 by 10, right? So e power t is basically 2 root 10 by root 11. Therefore, t is basically ln of 2 root 10 by root 11 will is basically equal to ln, this is 2 ln 2 divided by ln of 11 by 10, right? Very simple to say, and you want to know this amounts to 14.54 hours, 5451 hours, right? This calculation you can only do if you have a log table or if you have a calculator handy. And so in most exams, if you don't have this kind of a value, what they do is they generally accept these kinds of answers also. Right? You don't really need to provide the numerical. If you have the number ready though, you have to provide the numerical value because that is what carries marks. Fine. And the final question, number 23. General solution of the differential equation y dash equals e power x plus y is what? Right? Very simple. This is basically e power x into e power y. Right? So what you do is basically dy by e power y equaling e power x dx and taking integral on both sides. This is basically e power minus y. So this is minus e power minus y equaling e power x plus c, or basically e power x plus e power y equals c, right? Because minus of some arbitrary constant is also another arbitrary constant. Therefore, B is the answer. Wait, no, not B, not B, not B. A is the answer, right? Because it's e power minus. The answer is A, right? The answer is A, right? Thank you for listening. Have a good day.